Now we're going to say that a rational expression is complex if the numerator or the denominator, or both, contain another rational expression. So we've seen types of really complex fractional expressions already. So for example, we may have seen something like this, where our fraction contains another fraction inside the denominator. Now an example of a complex rational expression might be one of the following. So here we have a rational expression in the numerator and a rational expression in the denominator of our overall fraction. So this is our focus of this chapter. We're going to learn some techniques on how to simplify these particular rational expressions. The strategy that we're going to work with is the following. We're going to take a look at the numerator and try to simplify that into a single fraction. After we're finished with the numerator, we're going to take a look at the denominator and simplify that into a single fraction. Once we have the numerator and denominator both as single fractions, we can use the procedure for dividing rational expressions to simplify our current rational expression. This is best illustrated through a couple examples, so let's jump right in. So let's take a look at our first example. What I'm going to do is I'm going to rewrite our numerator over on the side. So our numerator is 1 plus 5 over y minus 2. And I'm going to focus just on simplifying the numerator to one single fraction. So what we do is we change our 1 to y minus 2 divided by y minus 2. And we're going to add to it 5 over y minus 2. So combining, we get y minus 2 plus 5 over y minus 2, or y plus 3 over y minus 2. This means that over on the left, we can rewrite our numerator as this single fraction, y plus 3 over y minus 2. Now I'm just going to recopy down our denominator. And that's going to be our next focus, is on trying to simplify this denominator. Our current denominator is 1 minus 2 over y minus 2. So let's try to simplify this one by switching up our 1 to a y minus 2 over y minus 2, and doing this subtraction. So here we'll have y minus 2 minus 2 more, and we're going to get y minus 4 over y minus 2. So what I'm going to do is I'm going to erase the work that I have on this slide, and I'm going to replace this denominator with the new fraction y minus 4 over y minus 2. Perfect. So this is our strategy. We try to simplify the numerator and denominator so that we get single fractions. So now we can think of this question as the following. Y plus 3 over y minus 2 divided by y minus 4 over y minus 2. So really, now what we've done is we've changed our question to a multiplication kind of question. We're going to switch out our division sign with the multiplication sign and flip our second fraction and multiply. So notice here that our factors of y minus 2 are going to cancel, and we're going to be left with y plus 3 over y minus 4. Here's our second example, and I'm going to first start working with the numerator. So here we know that the LCM of these two denominators is x times x plus 1. This means that the fraction on the left-hand side is missing a factor of x, so as I move from this fraction to this fraction, we're going to multiply both the numerator and the denominator by the value of x. The fraction on the right is missing the factor x plus 1, so as we move from this fraction to this fraction, we multiply both the numerator and denominator by x plus 1. Now that we have a similar denominator, we can go ahead and add our numerators together. And I'm going to just quickly simplify this numerator to 4x plus 1. So this means over on the right-hand side, we can replace this numerator with 4x plus 1 all over x times x plus 1. Next, let's go ahead and work on trying to replace our denominator. Once again, we're going to have the same LCM for our two polynomials. So we're going to convert this to a fraction whose denominator is x times x plus 1. Moving from this fraction to this fraction, we've multiplied by x in the denominator. That means the numerator also has to be multiplied by x. And over here, as we move from this fraction to this one, we've multiplied the denominator by x plus 1, so we need to also multiply our numerator by x plus 1. Now we have a little bit of work in the numerator to simplify. If we were to distribute through, we should get 3x plus 3. So I'm going to try to do this last step in my head here. I have 2x plus 3x is 5x. And there are no other numbers to add to our 3 once we get it. So the numerator should be 5x plus 3, and our denominator is x times x plus 1. So I'm going to erase all the work that we've done, and I'm going to replace this denominator with our new denominator on our next slide. And once we get to this step, we're just going to rewrite our complex rational expression using multiplication instead. So we're going to copy down our first fraction, and we're going to multiply by the reciprocal of our second fraction. Notice here that the denominator of our first fraction and the numerator of our second fraction will cancel, and our final answer is going to be 4x plus 1 over 5x plus 3. What I'd like to do in this last example is to show you an alternate strategy that you can use when the fractions in your numerator or denominator are fairly small. See here that the fractions inside of our numerator contain denominators that only have one term inside of them. When they're nice and small like this, sometimes it's easy to use the following strategy. The strategy is to multiply every single term inside of our big rational expression by the LCM of the denominators of our smaller rational expressions. So our smaller rational expressions are 5 over x, 6 over x squared, 6 over x, 5 over x squared. So if we can find the LCM of the denominators of these smaller fractions, then we have an alternate strategy to use. In this case, the LCM of x and x squared is x squared. So what we could do is we could multiply every single term by x squared and see what happens. I'm going to multiply 1 by x squared, I'll multiply this fraction by x squared, this fraction by x squared, and we keep doing that for every single term. And in red, I'm going to go through and work through the cancellations that happen. So over here, we see that we get 6x squared divided by x squared. So our x squareds here are going to cancel. The same thing is going to happen in the denominator here. Over here, we have x squared divided by x. So we are going to get rid of the 1x that's inside of our denominator. And we're also going to get rid of 1x inside the numerator. The same thing is going to happen down here. We can get rid of the x in the denominator and one of the x's inside our numerator. So now that we've done our cancellation, we have the following. X squared times 1 is x squared. X times 5 is 5x. Here we have 6 times 1, so we just get 6 by itself. In our denominator, we have x squared times 1 plus 6 times x plus 5. So let's go ahead and factor these quadratic expressions to see if anything's going to cancel off before we get to our final answer. So let's go ahead and factor our numerator. We need to find two values that multiply to -6 and add to -5. Well, those two values are 6 and 1. We need -6 and a +1. Next, we look for two values that multiply to +5 and add to +6. Those are going to be +5 and +1. From here, we see that we have a common factor that's going to cancel, so let's get rid of our x plus 1, and our final simplified form is going to be x minus 6 over x plus 5. All right, my little epsilons, stay positive.